4.5 gives you the integral of, so you jump here, -3 to 3, x cubed 4x squared minus 3x minus 6 dx. And it says write the integral as the sum of the integral of an odd function and the integral of an even function, and then use simplification to evaluate the integral. So it's, I think you could just actually do this integral, right? You could integrate x cubed and x squared and x and -6 and then plug in 3 and plug in -3. You could do it. It would be long and not necessary, but you could do it. What they're trying to get you to do instead is use the fact, you know, when you integrate an odd function, right? Odd functions are like x cubed, for example. If you integrate this guy, as long as your limits are symmetric, the area is going to cancel out. Right? If you go from, say, -3 to 3, this part will give you negative area, and this part will give you the exact same amount of area but positive. So it's going to cancel. So that's what happens when you integrate an odd function about symmetric limits. If you integrate an even function, you remember what happens? So like think x squared here.
So just double.
It doubles, right? If you go from -3 to 3, I guess, since I started with that. This area and this area are the same, so you can simplify your integral by going from 0 to 3 and then doubling. So in this case, what I'm going to do is split my function into an odd function and an even function. And the way you do that, well, all the odd exponents are going to make up an odd function, and all the even exponents are going to make up an even function. So this guy splits up into x cubed minus 3x as one of my functions. This is odd because it's a polynomial with all odd exponents. But then plus, I have to take care of my other two terms. Since this guy, you guys, this is an odd function, do you agree?
Yes.
Yes. How do you tell?
Because of the cube.
If you plug in a negative x, the negative doesn't go away. That's how you tell if it's odd. Right? When you plug in negative everywhere you see x, the negative pops outside. Whereas here, if you plug in negative x everywhere you see x, the negative goes away. So this guy's even, this guy's odd. Because this guy's odd, the picture you have in your mind is something like this. From -3 to 3, the area is going to cancel here. 0. This guy I can simplify a little bit by changing it into 2 times the integral from what to what. Instead of doing the integral from -3 to 3,
0.
I can just do 0 to 3 and double it. That helps me because when I start plugging in numbers, it's easier to plug in 0. So I keep this 2 on the outside, I do my indefinite integral, I find my antiderivative. This will become 4x cubed over 3 minus 6x, evaluated from 0 to 3. When I plug 3 in, I'll get 4 times 27 over 3 minus 6 times 3. And then I don't need to plug 0 in because, well, I mean, I can do it, but when I plug 0 in, it just ends up giving me 0. Because 0 cubed is 0, 0 times 6. So all that, so now I just have to actually calculate this out. So 2 times 27 over 3 is 9. 4 times 9 is 36. Minus 18. So 2 times 18. So, like I said, It's just trying to get you to simplify first so that you don't have to do as much work and start plugging numbers in. Make sense? You could do it without doing this, it's just tedious. Usually the more clever you are, the more time you can save yourself. And you can do this trick with any polynomial like this. You can always split it up into the things that have odd exponents and the things that have even exponents. That always works. And then you said 61? 63. Oh, gotcha. Exercise 64, graph function shown, use the differential equation in the given point to find the equation of the function. Okay, okay. So they give you this equation, dy dx equals 18x squared times 2x cubed plus 1 squared. Alright. Use the differential equation in the given point to find the equation of the function. Okay. So they have some graph there. Basically what they're saying is they give you this picture. And it goes through 0, 4. Looks, it's got some crazy squiggles in it. So something like squiggle, up here and squiggles again, like that. This is your function y equals f of x. What does this equation up here tell you about this function down here? Nothing or unrelated?
Slope.
Slope. Right? That's what the derivative always tells you. If you have the derivative of something, it gives you the slope. So, for example, if you plug in 0, you should get the slope of your function as 0. If you plug in -1, you should get the slope of your function at -1. Okay? So this tells you the slope of this. But, more importantly, how do you get from the derivative back to the original function? You antiderivative, right? To undo a derivative, to get from the derivative to the original, you have to do the antiderivative. So, to actually solve for the function y equals f of x, you integrate both sides. So if you know dy dx equals 18x squared times 2x cubed plus 1 squared, you can integrate both sides to find what regular y equals. Right? To get rid of the dy dx and just get back to y, you can integrate both sides with respect to x like this. When you do the integral of a derivative, it just gives you y. Okay? The integral of the derivative of y is just y. On this side, you have to do a little more work to calculate this integral. How do you integrate this function here?
Would you FOIL that out first?
Oh, would you FOIL that out first?
Use substitution?
You could FOIL it out first and it would work, it would just be kind of long. I would definitely try use substitution because the inside function here has derivative 6x squared, which is almost like this. So u sub should work really well here. And if you let u equal 2x cubed plus 1, then du dx, the derivative of u with respect to x, is 6x squared. So therefore du will be 6x squared dx. Which means up here, let's see, I have dx and then 18x squared. So how do I turn this 18x squared into a 6x squared? You can divide the 18 by 3. Right, if you want to turn 18 into 6, divide it by 3. But then you have to make up for it outside by multiplying by 3. this guy, oh my marker, you're so sneaky. So this guy right here is my du. Right, that's 6x squared dx. But then this guy in here is u cubed. Oh, I'm sorry, u squared. This guy's u, and then we have a square left over. So on the left, I said I'm going to get y, because when you integrate the derivative, you get the original function. On the right, it's going to turn into the integral of 3 times the integral of u squared du. So 3 times u cubed over 3 plus a constant. 3's cancel. U cubed is equal to 2x cubed plus 1 cubed. So my function y should be 2x cubed plus 1 cubed plus a constant.
In this case, it's 4, right?
Oh. So now we do have to solve for this constant. Right? I don't want to leave this general constant because I have a specific point I can plug in. But I don't think you get 4 for C. Right? Well, you have to plug in x equals 0 and set y equal to 4 and then solve. So if we go up here and solve for C,
3.
yeah, I think you get 3.
-3.
Oh! Negative
3. 4 minus 1.
Whoa, 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 whoa. Slow down, you guys are too fast for me. So, y is 4, x is 0, so 2 times 0 cubed plus 1 cubed plus c. So altogether it looks like I have 1, this is gone, so I have 1 cubed, so c, I'm getting 3. So my function would be y equals 2x cubed plus 1 quantity cubed plus 3. So that's the formula for this function. So if you're given the derivative of a function, we can now get back to the original function just by integrating both sides. In this case, the integration we use u substitution for, but that was just because it was in the u substitution section. What else can I do for you, math slaves?
Sorry, 41.
41. So number 41, 4.5, gives you the integral of cosecant squared x over cotangent cubed x dx. I want you to find the indefinite integral. So what do you need to notice here? What's the trick? I mean, you could go crazy and try to simplify this with trig identities. Maybe you could get somewhere. But in my mind, I'm thinking of this cotangent cube like this. And I'm thinking of the cosecant squared as the derivative of cotangent. Almost the derivative of cotangent, right? So you can probably do this integral by setting u equal to what? cotan x. Because then when you calculate du dx, the derivative of u, the derivative of cotangent is negative cosecant squared x. Which is almost what I have up here, so this is looking good. Du is negative cosecant squared x dx. I have cosecant squared in dx. So if I fix this up with a negative, by putting a negative out front, then I have exactly du. So on the top I have du. On the bottom I have u cubed. Should be able to handle that. So this will become negative on the outside, integral of du over u cubed. So to integrate that, we bring the u up. We add 1 to the power and divide. Negative out front still, plus a constant. Clean it up a little bit. This negative and this negative will become a positive. U can go back on the bottom. We need to get back to x's. So I plug in cotan x for u. Or if you wanted to be clever, you can make it 1/2 tan squared. Since cotangent is the reciprocal of tangent. What do you think? Woo! Awesome!
That was cool.
Very good! Thank you! You taught me something really good. No, that's probably not. That's okay. I'll pretend you think that. Live in my own little fantasy world. So I guess I'll move on to chapter 5.